Happy Monday, everybody. And this is the notes for conditional probability. So what we're looking at here is when we talk about conditional probability, then what we're actually sort of looking at is, are events independent, meaning they have no bearing on each other? So one event happening has no bearing on another event happening, or are they dependent? So today we're looking at dependent events, which is the harder one, and tomorrow we'll do independent events. So dependent events are events whose outcomes are affected by each other. So a really good example of dependent events is when you're doing something like you're drawing names from a hat, or you're drawing cards from a deck, and you're drawing these without replacing. Like maybe you draw two names, but you don't replace the first one. So it's drawing two cards, let's say is an example. So drawing two cards from a deck, without replacement. What basically is happening is, if you've got two probabilities, hanging on to that first card, and then drawing the second card, changes the total number of outcomes possible. So it changes the denominator of one of the probability statements that we're going to use. Okay? So what this would mean would be the second card drawn depends on what the first card was. So depends, dependent. And so then that relates to what we call conditional probability. So conditional probability is when the probability of one event occurring given that another event has already occurred. And so then we have a formula for this. So if event B depends on event A, then you're going to use this formula. The probability of A and B occurring is equal to the probability of A occurring times the probability of B occurring given that A has already occurred. Okay, so a couple things here. This is on your formula sheet. And this probability of B slash A, or that kind of straight line, that means the probability of B given that. So that that line straight up and down means given that A has occurred. And this is the version that's on your formula sheet, but sometimes you have to solve for the probability of just A or the probability of just B, so you can rearrange this by dividing both sides. So for example, that yellow will work very well. The probability, nope, that didn't work. Okay, let's look at the black. So we can say that the probability of B, given that A has occurred, is equal to the probability of A and B occurring divided by the probability of A. That's just like a way of rearranging it. Okay, so we are going to look at some examples of what this sort of means here. A computer manufacturer knows that in a box of 100 chips, 3 will be defective. Jocelyn will draw 2 chips at random from a box of 100 chips. We want to determine the probability that she'll draw 2 defective chips. So let's let A, I need to change my color here. Okay, so we're going to let A equal the first chip is defective. And let B equal that the second chip is defective. So the probability of the first chip being defective, right? We've got 3 chips out of 100. So we're picking that's 3 out of 100. The probability of B occurring given that the first chip was defective. So we reached into the bag, we picked a chip that was defective. So that means now we only have 2 chips left in the bag, or 2 defective chips left in the bag out of a total of 99 chips. So we basically, it just means that you account for that first event occurring. So we're assuming this has occurred. So then that changes the numerator and denominator of your probability statement. And then we can put those two together in our formula to figure out the probability of A and B occurring, because that's what we were trying to find, right? Was the probability that the first chip is defective and the second chip is defective. So that equals the probability of A occurring times the probability of B given that A has occurred already. So 3 out of 100 times 2 out of 99, which will give you 6 out of 9,900. And if you want to simplify that and put it in lowest terms, which you should, that gives you 1 out of 1650. Okay. You can also get there using the fundamental counting principle. Okay. So the probability of A and B occurring is equal to, let's put a line in there for our fraction, and then we're going to put lines in for our fundamental counting principle. We're picking 2 chips, and we want to know the total possible outcomes there. So the first chip, there's 3 defective ones. Once we've picked a defective one, there's only 2 left. There's 100 chips to begin with. Once we've picked one, there's only 99 left. So again, that gives us 6 out of 9,900, which simplifies to 1 over 1650. Okay, so we're going to look at calculating the conditional probability of a pair of dependent events. Nathan asked Riel to choose a number between 1 and 40, and then say one fact about the number. Riel says that the number he chose is a multiple of 4. Okay? And we want to determine the probability that the number is also a multiple of 6. So we're going to start by using a Venn diagram. So let me set up my Venn diagram here. I'm going to cheat a little, see if I can. And draw, oops, just a square, not square. Here we go. Probably would have been easier to just draw. Yeah, it is actually. Let's just get rid of this. Okay. I'm just going to draw a square. A Venn diagram. Okay, so if we call multiple of 4, that's going to be event A. Multiple of B, that's multiple of 6, that's going to be event B. We're trying to figure out the probability of A and B occurring. So remember that and always means the intersection means and, which means multiply. And that's what we're doing here. Then we have our 2 circles. Okay. So what we want to do is figure out what numbers go where. So we'll say that this is A and this is B. So A is multiples of 4. B is multiples of 6. So let's look at event A is 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. Okay, so those are multiples of A, or multiples of, 4 for event A. Event B is multiples of 6, 12, 18, 24, 30, 36. Okay, and so which ones are common to both? Let's see if we can squeeze them in. 12, 24, so that's a 20 there, and 36. So those go in the middle. 12, 24, 36, and then everything else can go in the appropriate circle. 4, 8, 16, 20, 24, 28, 32, and 40. And then we've got 6, 18, and 30. So the probability of B, given that A has occurred, is, look at that, we've got 3 choices. Out of 10. Because there's 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and there's 3 that we have in common, and we've got this going on here. Now, we could also do it this way, with the formula. Let's kind of go down to the formula, because you might find the formula a little bit easier to deal with in the Venn diagram. So probability of A and B occurring is equal to the probability of A occurring times the probability of B occurring given that A has occurred. Okay, so I didn't explain this up here very well. We've picked one of these numbers, right? We've picked something from A, so that means we have 10 total outcomes, right? So that's 10 outcomes, 10 numbers that we've chosen out of 40. That particular sort of number doesn't matter here. And of those 10 numbers, 3 of them are also factors of 6. So that's where the 3 out of 10 comes from. In terms of the formula, what we're trying to solve for here is the B given A. So we want to rearrange this formula a little bit. We're trying to solve for this. So the probability of B, actually let's, here, before I rearrange, let me actually just plug in what I want here. Okay, probability of A and B occurring is 3 out of 40, because there were 40 numbers, right? And that intersection is 3 out of a total number of 40. The probability of A occurring is 10 numbers out of 40, and then we're trying to find B given A. So the probability of B given A. And when we rearrange this, the probability of B given A is equal to 3 out of 40 divided by 10 out of 40, which, if we remember fractions, that's 3 out of 40 times 40 over 10. Cancel your 40s and you get 3 out of 10. So some of you might find the Venn diagram easier, some of you might find the formula easier. It's up to you. What I would like you to do now is try one on your own. So same thing, but now we're assuming that the number you picked first was 6. And we want to, or sorry, it was a multiple of 6. We want to know how many of those, once he's picked a multiple of 6, what's the probability that that number is also a multiple of 4. So you can pause this now, but the answer that you should get is going to be 3 out of 6 or 1 out of 2. Okay, and I have the work for that on the notes that the sub has if you want some help with that. Okay, solving a conditional probability problem. So according to a survey, 91% of Canadians own a cell phone. Of these people, 42% have a smartphone. Determine to the nearest percent the probability that any Canadian you met during the month in which the survey was conducted would have a smartphone. So C is going to be owning a cell phone. And S will be owning a smartphone. So the probability of owning a cell phone is 91%, or 0.91. And the probability of owning a smartphone, given that you have a cell phone, is 0.42. So we just want to figure out the probability that somebody would have a smartphone. Okay. So the formula we're using here is the probability of, oops, let me use the right stuff here. The probability of C and S is equal to the probability of C times the probability of S given C. This here is just equal to the probability of S, right? Because cell phone and smartphone, that's the same thing as just a smartphone. So it's a cell phone, but it's also a smartphone. So probability of S is equal to the probability of C times the probability of S given C. So we're just going to multiply those two probabilities together. The probability of having a smartphone is 0.91 times the probability of having a smartphone given that it's a cell phone, which is 0.42. So then your probability there is 0.3822 or 38.22%. So what I want you to do now is the your turn one. So determine to the nearest percent the probability that any Canadian you met in the month would have a cell phone but not a smartphone. And how could you represent this probability in a Venn diagram? Again, this one here, you should get 0.53 or 53%. Okay? And you can stop this and do the work through it. And again, the work for it is on the copy of the notes that I've left for the sub, and the same thing with part B for representing it in a Venn diagram, which I want to not draw the answer for. I want you guys to draw that. And then on the next page is the one more example. Making predictions that involve dependent events. So Hillary is the coach of a junior ultimate team. Based on the team's record, it has a 60% chance of winning on calm days and a 70% chance of winning on windy days. Tomorrow, there's a 40% chance of high winds, and there are no ties in ultimate. So we want to know the probability of Hillary's team that the team will win tomorrow. So we have a bunch of different things we have to look at because it depends on whether or not it's windy, right? And then we also have to look at what the chances are of it being windy. So let's write down some probabilities and do some terminology here. So we're going to say the probability that it's windy tomorrow. Let's just use, well, actually, no, I'll keep going. Never mind. Okay, the probability of windy tomorrow is equal to 0.4. So the probability that it's not windy tomorrow is the complement of that. So it's 1 minus 0.40, which is 0.60. The probability of a win, given that it's windy, is 0.7. So that means the probability that they lose, given that it's windy, is 1 minus 0.70 or 0.30. And then the probability that they win, given it's calm, is 0.60. So that means the probability that they lose, given that it's calm, is 1 minus 0.60 or 0.40. So what we're going to do here is we're going to use a tree diagram. And bear with me because it's going to take a few minutes to set up. But we're going to look at, our tree diagram involves two stages. The first stage looks at weather. And the second stage looks at, so for weather, it's either going to be windy or it's going to be calm. And we can put our percentages on there. The probability of it being windy was 0.4, and the probability of it being calm was 0.6. Then we're going to look at the result, so win or lose. So then for windy, they can win. For windy, they can lose. For calm, they can win. For calm, they can lose. And then we can fill in the appropriate probabilities there. So the probability that they win given that it's windy, was 0.7. The probability that they lose, given that it's windy, was 0.3. The probability they win, given that it's calm, is 0.6. And the probability they lose, given it's calm, is 0.4. So then what we can do here is we can figure out then what these probabilities are. So the probability, let's put in some stuff here, let's go this way. The probability of winning, windy and winning, is 0.4 times 0.7, which is 0.28. The probability of windy and losing is 0.4 times 0.3, which is 0.12. The probability of calm and winning is 0.6 times 0.6, which is 0.36. And the probability of calm and losing is 0.6 times 0.4, which is 0.24. So the question we were asked was the probability that they will win tomorrow. So that is, there are two circumstances for that, right? For winning, we've got windy and winning, calm and winning. So the probability of winning is equal to the probability of windy and winning plus the probability of calm and winning, which is 0.28 plus 0.36 or 0.54. Sorry, 64. Can't add. Okay, so then your turn here. So explain how you can check quickly to determine if Hillary made errors in her tree diagram. What you want to be is that the probability, like if you add these four probabilities together, you should get a certainty. So you can check that all probabilities add to 1. That would be checking that you've done your Venn diagram correctly. And then try question B, which says determine the probability that Hillary's team will lose tomorrow, and verify using another method, so whatever you want to do there. So I'll tell you that the probability is 0.36 is what you should get for that. Okay, so that's conditional probability. And your assignment for today, which I would appreciate if you actually worked on it instead of playing on your cell phones. It is in the textbook, page 188 to 191, numbers 1 to 20. Okay, and I'll see you tomorrow.